So much of our modern world feels, well, incredibly complex, almost magical sometimes.
Yeah.
Your phone giving you turn-by-turn directions or like online services recommending the perfect movie, even something as basic as calculating taxes, it just works because of these underlying systems.
Absolutely. Yeah, we interact with these systems constantly. And often, at their core is something that sounds both simple and maybe a bit intimidating, the algorithm.
Right. Algorithm, it's become such a buzzword. You hear the algorithm did this, algorithmic bias. But what is it actually,
It,
really?
exactly. It's a big question.
It's a term we hear thrown around all the time, often just vaguely meaning, I don't know, computer magic or something.
Hmm.
But it turns out algorithms have a very precise definition and a history that goes back way, way further than Silicon Valley.
Oh, much further.
And that's really our mission today. We're doing a deep dive looking closely at a single comprehensive source, a really thorough look from Wikipedia to try and cut through the
Yeah,
noise.
get to the core of it.
We're going to unpack the true definition, uncover that surprising history, explore the different types, and maybe most importantly, figure out why understanding algorithms actually matters to you.
Okay, sounds good. So let's start with that core definition then.
Yeah.
The source defines an algorithm as a finite sequence of mathematically rigorous instructions.
Mathematically rigorous. Okay, that sounds pretty strict, like it leaves no room for guesswork.
Precisely. That's the idea. It means the steps are completely unambiguous, they're precise, and they're designed for a clear purpose. Usually that's solving a specific class of problems or performing some kind of computation.
Uh-huh.
You can think of it maybe like a very detailed recipe or like a set of assembly instructions, but for handling numbers or data. It's really a specification for how calculations or data processing should happen.
So it's not just a general idea, it's a very specific step-by-step process with strict rules.
Exactly. And, while the basic idea is simple steps, algorithms can actually get quite sophisticated. Well, they can incorporate conditionals,
Hmm.
the if this happens, then do that kind of logic.
Right.
And that allows for automated decision making. They can even be designed to deduce valid inferences,
Hmm.
which gets into the whole area of automated reasoning.
Okay, so they can react and sort of make choices based on the inputs they get. Now, you hear the word algorithm used for things like, say, social media feeds or movie recommendations,
Mhm.
but those often feel less like precise instructions and maybe more like educated guesses. Is there a distinction there that the source talks about?
Yes, absolutely. And it's a really crucial one that often gets blurred in just everyday conversation. The source specifically contrasts algorithms with heuristics.
Heuristics. Okay, what's the difference?
Well, heuristics are approaches you use to solve problems where there isn't necessarily a single mathematically well-defined correct or optimal result.
Ah,
Social media recommendations are a perfect example. There's no single best video for everyone.
right.
Uh-huh.
Makes sense.
So the system uses heuristics, rules of thumb, patterns, likelihoods, to find a good enough solution, not one that's guaranteed to be optimal in a strict mathematical sense. Okay. That clears things up a lot. So algorithms are aiming for that rigorous, often optimal result or computation,
Exactly.
while heuristics are more about finding practical, workable solutions when optimal isn't really possible or maybe even needed.
Right. And for a procedure to really count as an effective algorithm based on these definitions, it needs some key properties.
Like what?
It has to use a finite amount of time and space resources. It needs to be expressed in a clear, well-defined, formal language. It starts with some initial state and input, moves through a finite number of defined steps,
Yeah.
produces an output, and crucially, it has to terminate. It has to actually finish.
No endless loops allowed.
Exactly, no infinite loops. Although the source does mention a distinction between deterministic algorithm,
Oh,
which make exact predictable decisions at every step, and randomized algorithms, which actually intentionally incorporate random input. So randomness can be part of the plan, even a rigorous plan.
it can, yeah. It sounds counterintuitive, but it's a valid technique.
Interesting. And while we naturally think computers today when we hear algorithm, you mentioned they don't have to run on silicon.
Not at all, no. The algorithm is the logical procedure itself. It's kind of independent of the machine executing it. The source notes, they can be found in biological systems like neural networks in the brain,
Yeah.
in electrical circuits, even in purely mechanical devices. The steps are the algorithm. The hardware is just the thing that carries them out.
Okay, that gives us a really solid foundation for what an algorithm is. Now, this is where I think it gets really interesting. The history. You said this concept is ancient.
Oh, much, much older than most people probably realize. The word algorithm itself It has a direct link back to a Persian scientist, Muhammad ibn Musa al-Khwarizmi. This was around 825 AD.
Al-Khwarizmi. Okay, how did his name get connected to the word itself?
Well, his works, particularly on the Hindu-Arabic numeral system,
Mm.
the numbers 0 through 9 we use today, they were translated into Latin in the 12th century.
Mm-hmm.
And in those translations, his name got Latinized as Algorismi or Algorismi.
Algorismi.
Yeah. And apparently one famous text even starts with the phrase Dixit Algorismi, which means thus spoke Algorismi.
Thus spoke Al-Khwarizmi. That sounds like something out of an ancient scroll.
It basically is. And initially, in English, the word algorithm with an asm at the end specifically meant doing calculations using this new place value notation, which is what his big contribution was about in those translated works.
Oh, okay.
We actually see the word appearing in English writings way back in the 13th century. Even Chaucer, in the late 14th century, mentions Aughrim stones, which were likely used for decimal calculation.
So algorithm was specifically about decimal arithmetic back then.
Primarily, yes. But the word evolved. Later, in the 15th century, probably influenced by the Greek word arithmos, which means number.
Mm-hmm.
It got altered slightly to algorithmus. And that eventually gave us the modern spelling algorithm by around 1596 in English.
Wow, so the word itself is this fascinating blend of Persian and Greek history. But the idea, the core concept of a step-by-step procedure for a mathematical problem that's much older even than Al-Khwarizmi, right?
Well, absolutely.
Yeah.
Way older. This fundamental idea of breaking down a problem into structured, repeatable steps seems to have emerged independently in many different ancient cultures. We find evidence in Babylonian mathematics going back as far as 2500 BC.
2500 BC?
It really puts it in perspective, doesn't it? They had procedures for division, for calculating formulas. We also see it in Egyptian math around 1550 BC. In Indian mathematics starting around 800 BC, with things like the Shulba Sutras and later the Kerala school.
Mm-hmm.
Even the Ifa oracle, which is an African divination system, apparently used algorithmic processes around 500 BC.
So it wasn't just math, it was other logical systems too.
Seems like it. And of course, Greek mathematics gave us some really famous examples like the sieve of Eratosthenes for finding prime numbers.
Right, I remember that one.
And the Euclidean algorithm for finding the greatest common divisor. Both of those are from around 300 BC. Then you have examples in Chinese math around 200 BC, and of course Arabic mathematics around 800 AD, which brings us back full circle to Al-Khwarizmi.
Wow, so it wasn't just confined to one region or culture, it was like this fundamental human approach to problem solving that just popped up globally.
It really seems that way, and it wasn't always just for pure math either. The source points out Al-Kindi, who was a 9th century Arab mathematician.
Okay.
He developed the first known cryptographic algorithm using frequency analysis to break coded messages. Basically, the very first code-breaking algorithm.
That's a really powerful application right there, using structured procedures to unlock secrets. Okay, so how did this ancient global concept eventually evolve into the algorithms that are running, our digital world today?
Well, a really key intermediate step was the invention of the weight-driven clock back in the Middle Ages.
A clock, how does that connect?
Because it was seen as an accurate automatic machine. It was mechanical, precise, and followed a process. This idea of automation of mechanical processes, it sort of sparked imaginations. It led to mechanical automata like clockwork figures, and eventually, much later, to mechanical computational machines. Charles Babbage's difference engine and analytical engine in the mid-19th century are probably the most famous examples.
Right, Babbage, often called the father of the computer. And didn't he have a collaborator who was thinking very algorithmically for his machine?
Yes, absolutely. Ada Lovelace. She designed an algorithm specifically intended to run on Babbage's analytical engine, a machine that was never fully built in their time, but the concepts were there. And because the analytical engine is widely seen as the first design for a general-purpose Turing-complete computer, Ada Lovelace is often called history's first programmer.
History's first programmer, Ada Lovelace. That's a fantastic detail, connecting that mechanical age right into the computational age.
Yeah, it's a great link, and the thread continues, through things like electromechanical technology. Think telephone switching exchanges.
Oh, okay.
That kind of tech inspired engineers to think about logical steps, but using electrical circuits instead of gears. This led figures like George Stibitz, working at Bell Labs, to build digital adding devices in 1937. He was literally tinkering at home, apparently, building a binary adder because the mechanical calculators they had were too slow and clunky.
So from clay tablets and clockwork through gears and telephone switches to electrical circuits and finally digital adders. It's really this continuous story of automating processes.
It is. It really highlights that the core idea is about the process, the logic, not just about the computers themselves, which brings us neatly into the 20th century and a major shift, the push for formalization.
Making the whole concept mathematically airtight, putting it on a really solid foundation.
Exactly. It really picked up steam around 1928 with a famous problem posed by David Hilbert called the Entscheidungsproblem, the decision problem. The goal was basically to formally define what effective calculability or an effective method truly meant. Could we create a definite procedure to decide if any mathematical statement was provable?
So trying to put rigorous boundaries around what can actually be computed, period?
Right. And this quest led to several incredibly important formalizations in the 1930s that are still absolutely core to computer science today. You had Gödel Hildebrand clean recursive functions, Alonzo Church's lambda calculus, Emil Post's Formulation 1, and maybe the most famous one, Alan Turing's Turing machines, developed in 1936 and 37.
Turing machines, right.
These different models developed independently all turned out to be equivalent in power, and they provided that rigorous mathematical basis for defining exactly what an algorithm is and what it can compute.
Okay, so once you have this formal, rigorous idea, how do you actually write an algorithm down so that other people or machines can understand and use it?
Right. Well, algorithms can be expressed in lots of different ways. You can use natural language, like English. But, as you might guess, it's often just too verbose, too ambiguous, especially for complex technical procedures.
Yeah, too much room for misinterpretation.
Exactly. So more structured methods were developed specifically to avoid that ambiguity. Things like pseudocode,
Okay.
flowcharts, Draken charts, control tables. These provide more structure. And, of course, today, programming languages are the primary way we express algorithms. They're designed specifically for computer execution, but they also serve as a way to define and document the algorithm itself.
Right. Pseudocode and flowcharts are pretty familiar ways to visualize the steps. The source also mentioned different ways to describe Turing machine programs specifically.
Yeah, talks about different levels of description you might use for a Turing machine program. There's a high-level description, which focuses more on the algorithm's purpose and qualities without getting lost in the mechanical details.
Okay.
Then there's an implementation description, which shows the general mechanics, how the machine head moves, what it writes, etc. And then there's the formal description, which is the most rigorous. It gives the exact state table, defining every possible move.
So layers of detail depending on what your purpose is. And the flowchart was highlighted as a key graphical tool.
It is. Flowcharts use those standard symbols. Arrows show the flow, rectangles are for steps or actions. Diamonds represent decisions, the IF then LC logic. Dots can show where paths merge, like an OR. They really provide a visual map of the algorithm's logic and how control flows through it.
Okay, so we know what they are, roughly where they came from, how to write them down. Now, how do we figure out if one algorithm is actually better than another for doing a particular job?
Yeah, that's where algorithmic analysis comes in. It's basically the whole field dedicated to figuring out how much time, storage space, or other resources an algorithm requires to run. And usually that's measured as a function of the input size.
So how fast will it finish, and how much memory will it chew up, depending on how much data you feed it?
Exactly. And quantitative methods are used for this, with big O notation being the standard way to express it.
Big O. Okay.
Yeah, big O notation tells us essentially how the algorithm's resource usage scales as the input size, which we usually call n, gets bigger. For example, a simple algorithm that sums up a list of n numbers, that takes O(n), the time grows linearly with the size of the list.
Makes sense. Double the list, double the time, roughly.
Pretty much. And the space it uses might be O1, constant space, or maybe ON space, depending on exactly how you implement it.
So ON, OMN, ON squared.
Yeah.
These notations are like a shorthand for how efficiently an algorithm scales up.
Right. And this scaling behavior is absolutely crucial for comparing algorithms. The source gives a great classic example, searching for an item in a sorted list.
Okay.
A simple sequential search, just checking each item one by one, is ON. On average, you might have to look at everything.
Right.
But a binary search, where you keep dividing the search interval in half.
Jump to the middle, see if it's higher or lower.
Exactly. That approach is O log n, logarithmic time.
And O log n is way, way faster than O log n gets large, right?
Hugely faster. For a list with 1 million items, O log might take 1 million steps in the worst case. O log n takes about 20 steps.
20. Versus a million. Okay, yeah, that difference is dramatic.
It really is. That's why choosing the right algorithm with the right efficiency characteristics matters so much, especially for large data sets.
So how do you do this analysis? Is it all theoretical or do you test it?
Well, both, really. Analysis can be formal, where you study the theoretical properties, often using pseudocode and mathematical reasoning, or it can be empirical, where you actually implement the algorithm and test it on specific hardware and software, measuring its performance.
Formal sounds like the ideal case. Maybe. Empirical is more like the real world.
Kind of. Formal analysis gives you theoretical guarantees about performance, how it should scale. Empirical testing helps you see how it actually behaves in practice. It can reveal things formal analysis might miss, like how the processor's cache affects performance, or other unexpected interactions with the system. So both are valuable, but empirical tests usually complement formal analysis. They don't really replace it.
Makes sense. Theory and practice working together. And even well-established algorithms can still be improved upon. It's not like everything's figured out.
Oh, absolutely not. The source mentions a really interesting recent example, an innovation in fast Fourier transform algorithms, FFTs.
FFTs, right, used in signal processing, images.
Exactly. Things like medical imaging, audio processing, tons of stuff. This particular innovation apparently led to performance improvements of up to 1,000 times faster for certain tasks.
1,000 times. That's not just like tweaking it. That's transformative.
It really is.
Yeah.
And speedups like that have enormous impact. It's not just saving time. It can allow devices to use dramatically less power. Think about portable medical equipment or cameras or anything battery-powered. Efficiency is key.
Yeah, absolutely.
And when we analyze performance, we often look at the extremes, the best case and the worst case scenario for an algorithm.
The easiest possible input versus the hardest possible input.
Exactly that. The best case is the scenario that takes the absolute minimum time or resources. The worst case requires the maximum. Understanding these bounds is really essential for predicting how an algorithm is likely to behave under different real-world conditions.
Okay, so that's how we analyze how good an algorithm is once we have it. What about the process of designing one in the first place? Coming up with the steps.
Right, so algorithm design is really the creative but also mathematical process of actually devising the algorithms to solve problems. It often draws on various established solution theories or design patterns.
Design patterns, like in architecture or software engineering.
Yeah, similar idea. There are known strategies or templates for tackling certain kinds of problems. Think of things like divide and conquer or dynamic programming. These are overarching design approaches.
Okay.
And a critical goal, always, in design is resource efficiency. Again, measured using big O notation. You don't just want an algorithm that works. You want one that works efficiently with the resources it has.
So efficiency needs to be baked into the plan right from the start. The source also mentioned structured programming in this context. How does that fit in?
Yes, structured programming is really a design philosophy that became influential in the 60s and 70s. It basically advocates for building programs using only a few fundamental control flow structures.
Like what?
Things like sequence, just doing steps one after another, if then else, making choices, while do or dual looping, maybe case for multiple choices.
Okay, the basic building blocks.
Exactly. The main goal was to avoid the tangled mess that can come from undisciplined use of GOTO statements jumping around arbitrarily in the code. That often leads to what people call spaghetti code.
Right. Hard to follow, hard to debug.
Very hard. Structured programs built from these simple blocks tend to be much easier to read, understand, reason about, and maintain. And importantly, they lend themselves much better to mathematical proofs of correctness.
Proofs of correctness. You mean proving mathematically that the algorithm will always do what it's supposed to do.
Precisely. Proving that it will produce the correct output for all valid inputs and that it will terminate. That's much easier to do with clean, structured logic than with tangled spaghetti code.
Yeah, those proofs sound incredibly important, especially as algorithms get more complex and control more critical things. Now let's shift gears slightly to a more maybe controversial topic mentioned in the source. The legal status of algorithms. Can you actually patent an algorithm?
Yeah. This is a really complex and frankly pretty debated area, especially in the US. The general stance is that algorithms by themselves, just the abstract mathematical procedure or formula, are considered abstract ideas and are therefore not patentable subject matter.
So the pure idea isn't property you can own.
Correct. You can't patent Ease in SOC or the idea of binary search in the abstract. However, practical applications of algorithms can sometimes be patented.
How does that work?
The source references a key Supreme Court case, Diamond v. Dyer. In that case, using a known mathematical algorithm as part of a larger industrial process for curing synthetic rubber was deemed patentable. It wasn't the algorithm itself they patented, but its specific application within that physical process.
Okay, so applying the algorithm to a tangible, real-world machine or process might be patentable, but not the abstract steps alone.
That's generally the line, yes. Though the whole area of software patents, which obviously heavily involve algorithms, remains pretty controversial. Some specific patents that cover algorithms, like one for LZW data compression, have faced a lot of criticism over the years. And the source also notes that some types of algorithms, particularly strong cryptographic algorithms, can be subject to export restrictions by governments.
Right, national security concerns.
Exactly. So while the pure abstract algorithm might not be patentable, its implementation, its specific uses, can definitely have significant legal and regulatory implications.
It really highlights that algorithms aren't just these abstract mathematical things. They have real-world impact that bumps up against laws and regulations. Okay, so given this incredible range of algorithms, how they're implemented, designed, the source lays out different ways to classify them, right? To categorize them.
It does, yeah. And there are several different ways you can slice it, different lenses to view them through. One major way is by implementation, basically, how they are actually structured and executed.
Okay, what falls under implementation?
Well, here you see classifications like, first, recursion versus iterative. Does the algorithm solve a problem by calling itself with smaller inputs? That's recursive, like the classic Tower of Hanoi puzzle. Or does it use loops and repetition? That's iterative. Often, you can express the same logic either way.
Okay, recursive or looping?
Then, serial, parallel, or distributed. Does it run just one instruction at a time on a single processor? That's serial. Or does it break the problem into pieces that can run simultaneously on multiple processors? Parallel. Or even across multiple machines connected by a network, distributed. Parallel and distributed have overheads, like communication, but can be much faster for some problems. Some problems, though, are inherently serial.
Right, can't be easily broken up.
Also, deterministic or non-deterministic. We touched on this earlier. Does the algorithm make exact, predictable decisions at every step? Or does it incorporate randomness or some form of guessing, maybe guided by heuristics?
Okay.
And exact or approximate. Does it guarantee finding the precise, optimal solution? Or does it aim for a solution that's just close enough? Approximate algorithms are essential for many really hard problems, NP-hard problems like the infamous knapsack problem, where finding the exact solution would take an impractically long time.
Okay, sometimes good enough is the only practical answer.
Exactly. And finally, under implementation, there's a newer category, quantum algorithm. These are designed specifically to run on quantum computers, using principles of quantum mechanics like superposition and entanglement.
Okay, so that's classifying by the nuts and bolts of how the computation happens. What's another major way to look at them?
Another really important classification is by design paradigm. This focuses on the fundamental strategy or the overall approach used to solve the problem. It's more about the method of attack.
So the core problem-solving technique being used.
Exactly. Think of these as different strategic blueprints, like brute force or exhaustive search. This is the straightforward approach. Just systematically try every single possible option until you find the solution. It's simple, also easy to implement, but can be incredibly slow for anything but small problems. Think password cracking by trying all combinations.
Right, guaranteed to work eventually, but eventually might be the heat death of the universe.
Pretty much. Then there's divide and conquer. This is a really powerful one. You break the main problem down into smaller, independent subproblems of the same type, solve those recursively, and then combine their results to get the final answer. Merge sort is a classic example. A related, sometimes simpler variant is called prune and search, where you solve the problem by reducing it to just one smaller subproblem, like in binary search. You don't need to combine results.
Okay, break it down or prune it down.
There's also search and enumeration. This covers strategies for exploring large possibility spaces, often visualized as graphs. Think about algorithms for playing games like chess or finding paths. Techniques like backtracking or branch and bound fall under here.
Exploring the options systematically.
We mentioned randomized algorithms before, deliberately using random choices during computation. This is often done to get good approximate solutions quickly, especially when finding the exact best solution is too hard. The source mentions two types, Monte Carlo algorithms, which have a high probability of giving the correct answer, but might occasionally be wrong, and Las Vegas algorithms.
Like gambling.
Sort of. Las Vegas algorithms always give the correct answer, but The amount of time they take is probabilistic. It might vary randomly. This whole area connects deeply to fundamental questions in computer science theory, like the P versus NP problem.
Right, the million-dollar question.
Another paradigm is reduction of complexity, sometimes called transform and conquer. The idea here is to transform your difficult problem into a different problem that you already know how to solve efficiently. Like, if you need to find the median element in a list, one way is to first sort the list, a solved problem, and then just pick the middle element.
Clever. Turn it into something easier.
And backtracking. This is used often in search problems. You build up a potential solution step by step. If you reach a point where you realize the current path can't possibly lead to a valid solution, you backtrack, undo the last step, and try a different option.
Trying paths and backing up if they're dead ends. Wow, that's a whole toolbox of different strategies. Are there specific paradigms tailored just for optimization problems? You know, where the goal isn't just an answer, but the best possible answer.
Yes, definitely. Optimization is a huge field, and it has its own set of key design paradigms. One is linear programming. This applies when you're trying to find the best outcome, like maximum profit or minimum cost, for some linear function, subject to a set of constraints that are also linear inequalities. The simplex algorithm is a famous method here, used for problems like finding the maximum flow through a network. There's also integer programming, a variation where the variables have to be whole numbers.
Okay, for linear relationships.
Then there's dynamic programming. This is super powerful. It applies to problems that have two key properties. Optimal substructure, meaning an optimal solution to the whole problem contains optimal solutions to its subproblems, and overlapping subproblems, meaning you end up needing to solve the same smaller subproblems many times. Dynamic programming avoids recomputing these subproblems over and over by storing their results the first time, a technique called memoization or caching. The Floyd-Warshall algorithm for finding all pairs' shortest paths in a graph is a great example. It often dramatically reduces the complexity, maybe from exponential down to polynomial time.
Solve it once, store it, reuse it. Smart.
There's also the greedy method. This approach makes the choice that looks best at the current moment, hoping that a series of locally optimal choices will lead to a globally optimal solution for the whole problem.
Just grab the best thing right now.
Pretty much. For some problems, like finding a minimum spanning tree in a graph using algorithms like Kruskal's or Prim's, this greedy approach actually works perfectly and finds the true optimum.
Ah, okay.
But for many other problems, a greedy strategy might get you stuck in a local optimum, a solution that looks good nearby but isn't the overall best solution possible.
So it can be short-sighted sometimes.
It can be, yes. And finally, the heuristic method. We talked about heuristics earlier. For optimization, this means finding solutions that are hopefully close to the optimal one, especially when finding the absolute optimum is computationally infeasible. These methods often involve iterative improvement or sophisticated search techniques like local search, taboo search, simulated annealing, or genetic algorithms.
Ways to explore and find good enough answers.
Exactly. They often get better over time, finding progressively better solutions. And if you can mathematically prove a bound on how far the heuristic solution might be from the true optimum, then it's called an approximation algorithm.
Okay, so depending on the exact problem, whether you need a perfect answer or just a good one, or you're trying to optimize something specific, there's likely a whole family of algorithmic strategies that have been developed and studied. It's definitely not just one kind of thinking.
Not at all. It really shows the incredible depth and variety within the field. And, just to make all this a bit more concrete, maybe we can look at that simple example provided in the source, the one about finding the largest number in a list.
Yeah, that sounds good. A basic illustration. Okay, walk us through that algorithm.
Okay, so first, the high-level description, just in plain English, easy to understand. First step. If the list you're given is empty, well, then there's no largest number, so you're done.
Makes sense.
2. Otherwise, if the list isn't empty, assume the very first number in the list is the largest one you've seen so far, just temporarily.
Okay, start with the first one.
3. Then go through each of the other numbers in the list, one by one.
Look at the rest.
4. For each number you look at, compare it to the number you're currently holding as the largest seen so far. If this new number you're looking at is bigger, then you update your largest seen so far. You replace the old one with this new, bigger number.
Keep track of the biggest one found yet.
5. Once you've gone through every single number in the list this way, the number you're currently holding as the largest seen so far must be the largest number in the entire list. So that's your answer.
Simple logical steps. Yeah, anyone could follow that process.
Exactly. It's clear and finite. Now, if we express that same logic using the quasi-formal description, the pseudocode given in the source, it looks like this. Algorithm, largest number.
A list of numbers L.
The largest number in the list, L. If L size equals 0, return null. Handle the empty list case. Largest L00 and 0s. Assume the first element is the largest initially. For each item in L, do loop through every item in the list. L if item largest, then check if the current item is greater than the largest found so far. Largest item. If yes, update largest to this new item. Return largest. After checking all items, return the final largest value.
Okay, yeah, that looks much more like code, but you can still clearly see those same steps we just talked about. Handle the empty case, initialize largest L0, loop for each, compare if item largest, update largest item, and finally return the result.
Right. The symbol just means assignment. For each sets up the loop, if then handles the conditional logic. It precisely lays out those finite steps, defines the input, list L, the process, and the guaranteed output, the largest number, or null. It's a fundamental algorithm, pretty simple, but it has all those core properties we discussed earlier: finite steps, clear instructions, termination whether a person follows it or a computer executes it.
So reflecting on this whole deep dive then, we've kind of journeyed from, wow, ancient Babylonian clay tablets and medieval clockwork
Yeah.
through these really rigorous formal mathematical definitions, different ways to write down logic, all the way to modern computer code and these pretty sophisticated classification systems for different strategies.
We really have. And I think the big takeaway is that algorithms aren't just some kind of complex, opaque computer magic. At their very heart, they are fundamental, mathematically rigorous procedures for solving problems or performing computations. And that's true whether the procedure itself is dead simple, like finding the largest number, or incredibly intricate.
And their history, that long history, it really reveals they're a core part of human ingenuity, right? A way we've seemingly always tried to bring structure, order, and efficiency to tasks and information processing.
It seems deeply ingrained.
So understanding algorithms isn't just for computer scientists anymore. It feels like it's becoming essential for understanding the logical steps that structure our information, solve problems, automate tasks, and increasingly make actual decisions in the world all around us.
They are truly the hidden instructions, the hidden logic, powering so much of our daily lives now, more and more every day.
And, that really raises an important question, maybe something for you, the listener, to consider. We've seen how algorithms can be used for automated decision-making, from really simple calculations all the way up to potentially complex judgments. Given their increasing complexity and how absolutely pervasive they are becoming in our lives, often hidden from view, what does it really mean for us, for society, to ensure these hidden sets of instructions are designed and used responsibly and transparently?